So, really, problem number one just requires you simplifying what they gave you. So, what they gave you is the following. And it's going to be helpful, of course, to distribute the A into these parentheses and the -5 into these parentheses. So, let's go ahead and just do that. I'm going to draw these arcs to just symbolize the fact that we're doing that. On the next line, it would be 4A minus A squared minus 5A minus 35. And at this point, we have a 4A and a -5A, so those are like terms. Those can definitely be combined. Now, I'd rather write this expression in such a way that the exponents are descending. So we're going to have that negative A squared first. And after combining the 4 and the -5, it's going to be minus A. And then finally, we will have that negative 35. And that corresponds to answer choice C. So that's how you do with that one. Moral of the story with this one, distribute the A, distribute the -5. Definitely remember that when you distribute that -5, it's going to multiply to the +7, and that's going to be a -35. So you do have to be careful with the signs somewhat. You also might want to consider just putting the term that has the exponent of 2 out front so that you have that nice descending order. And that does indeed show up in the answer choices like that. For problem number 6, I'd say it's important to remember that most numbers are not perfect squares. So we're very used to these perfect squares like 25 or 64 or whatever, where when you take the square root of it, it just ends up being some nice number like 5 or 8 or something, or -5 and -8. So we're used to that, but we need to remember most numbers are not perfect squares, right? If you take the square root of most numbers, you're going to get some crazy decimal, such as the one that they gave you, 9.2371. Okay, so you do need to remember that. Now, apparently, we took the square root of some number, we'll call it x, and we ended up with 9.2371. So it then stands to be the case is that 9.2371 squared gives you x, right? In the exact same way that the square root of 25 equals 5, and therefore we know for a fact that 5 squared must therefore equal 25. Okay, so if that's true, well, this is true. Okay, and the bottom line is what we could do is just realize, well, 9.2731, which I'll write right here, 9.2371. Well, that's most definitely in between two numbers. One number is 9, and the other number is 10. And what you could do is the following analysis. You could realize that, okay, well, we know that the answer is what you get when you square 9.2371. And after squaring it, it goes and turns into, 9.2371 squared. I'm just going to write that. After squaring 9, though, I mean, that becomes 81. And after squaring 10, that becomes 100. So in the same way that 9.2371 is between 9 and 10 before you square it, well, after you square it, whatever this number is, which we don't know yet, I mean, it's x, it's going to be between 81 and 100. Okay. Now, the problem asks the certain numbers between what two integers? Well, it's between 81 and 100, but you could also say it's between 81 and 99. Now, just in case you're worried about this 100, I mean, it's not 99, I understand that, but just remember 9.2 rounds down to 9. So when you square it, it's going to be like a little bit closer to 81, if that makes sense. Okay. Since 9.2 rounds down to 9, it's closer to 9 than it is to 10. So when you square it, it's going to be, the result's going to be a little bit closer to 81 than it will be to 100. So it's safe to say that, 9.2371 squared is between, 81 and 99. Okay. So that's why. That's my smiley face. Kind of a weird eye, but it's okay. That's why K is the answer. K is the answer to this problem. Functions tend to be challenging for a lot of students. It turns out that, after practice, they not only become relatively easy, but they might even become fun, dare I say. Now, some of you might disagree with that, and I understand. But nonetheless, we're going to walk through this one. Pretty straightforward function problem, actually. We got negative 4x cubed minus 4x squared. And at the end of the day, they just want f of negative 4. Okay. Now, I'm a big fan of using parentheses a lot. And what I like to do is remember, okay, if I'm going to do one of these function problems where it's like x turns into a negative 4 over here, well, I'm going to rewrite the original function just with a bunch of empty parentheses where x used to be. I just do that first because I know I'm going to be filling up the parentheses with something. And namely, it's going to be negative 4, right? So we're going to do that right now. Negative 4 goes there and negative 4 goes there. I did a little typo, that's a 3. Okay, so we have negative 4 times negative 4 cubed minus 4 times negative 4 squared. So it is the case that it is this entire blue negative 4 that's being cubed right now. And I'm going to want to attend to that soon. I'm also going to want to attend to this negative 4 squared. And the reason why I need to worry about that first is because of PEMDAS. PEMDAS. So PEMDAS is the order of operations. Some of you might have learned a different acronym, but this is a pretty common one where basically P stands for parentheses, E stands for exponent, M stands for multiplication, D division, A addition, S subtraction. And the P basically means like if there's an opportunity to simplify something that's inside parentheses, then go ahead and do that first. So for example, if you had something like 3 plus 5 minus 2, well, the P says, square away this 3 plus 5 thing. Okay. If there's an opportunity to simplify something inside parentheses, go ahead and do that first. Then move on to subtraction. In this case, it would be 6, obviously, right? So let's kind of draw an X through that to remind ourselves that that actually has nothing to do with this. So P comes first, but then there's E, and E says exponents. And that basically says if there's an opportunity to apply an exponent, do that before you do anything else, before you do multiplication, division, addition, and subtraction. Well, that is the case here. We can apply the exponent of 3. We can apply the exponent of 2. When you apply the exponent of 3, let's keep in mind, anytime you have a negative number cubed, it's going to remain negative. Okay, I'll say it again. Anytime you have a negative number cubed, it's going to remain negative. In fact, anytime you have a negative number raised to an odd exponent, it's going to turn out to be a negative result. Okay, anytime you have a negative number raised to an even exponent, it's going to turn positive. So that is worth making a mental note of for sure. So, um, so we know this is going to be negative, right? We know it's going to be negative, but what's it going to be? It's like, okay, 4 cubed. What is that? 4 times 4, which is 16, times another 4, which is 64. Okay. Now, I don't want to like do too much, so I'm just going to write this negative 4. And actually in blue, I'm going to write down what negative 4 cubed turned into. And what it turned into is negative 64. We're going to worry about that later. Let's keep in mind this is multiplication happening right here. I'm also going to preserve this -4 thing, and we're going to kind of analyze this. -4 squared is +16. I'm going to write that in blue as well, because that's what it just turned into. -4 squared is +16. Now we're going to worry about, what's going on the next line. So first of all, we have a negative times a negative, so we know it's going to be a positive, okay? Then the question is, okay, well, what's 4 times 64? So that's 256, so it's going to be a positive 256. And looking here, we got -4 times 16, which really is -64. And then finally, the answer is just 256 minus 64. Looking at the answer choices, what do we have? That would be 192. And that is J. Boom. That's how you do that one. So they give us a pretty weird looking system of equations, unfortunately. So I'm going to draw that right now. We have x plus 2y equals 4. Now it's possible we might want to use the elimination method for these. So I'm going to stack, the x's over the x's and all that stuff. So we got negative 2x plus y equals 7. Um, Yeah, so I'm a big fan of using substitution when there is, an x kind of by itself with a coefficient of an invisible one, or a y by itself with a coefficient of an invisible one. I'm actually going to work with this one. I mean, it really doesn't matter which one you work with, but I'm going to temporarily solve for y, so to speak, by adding 2x to both sides. So we end up with 2x plus 7. Okay, now in case you're confused about that, all I did was add 2x to both sides of the equation, and then I end up with y equals 2x plus 7. So what I'm going to do is just work actually now with these two equations, okay, in yellow, these guys, okay. So I just upgraded that to that, and as many of you know, if you're going to use substitution, all you have to do is plug 2x plus 7 in for this y. So I'm going to keep this in red to keep it color coded. We got x plus 2 times something equals 4. Well, what is that something? That something is 2x plus 7, which comes from here. And now we're just going to go red all the way around. We got x plus, after distributing, it's going to be 4x plus 14 equals 4. 5x plus 14 equals 4, right? 5x because we're combining these, but let's just go ahead and subtract 14 from both sides. It's going to be 5x equals 4 minus 14 is negative 10. So we have, dividing both sides by 5 gives us x equals negative 2. And the only answer choice that features negative 2 as the x coordinate or as the x term is answer choice A. So we are done. Now, some of you might be confused about this one because maybe you're used to doing systems of equations where it's like, oh, x equals something and then y equals something, and it's like this whole algebraic thing. And I totally get that. But I will say that we need to remember that when you're solving systems of equations, I mean, what you're really doing is you're taking a look at this equation, you're taking a look at this equation, and in a way, you're imagining what the graph of this equation would be, and you're imagining what the graph of this equation would be. And the so-called solution is the place where the graphs intersect. So in the case, certainly of these, linear graphs, that's a line if you were to graph it. That's a line if you were to graph it. The point of intersection would literally be a point. It would be a point. And when you solve for x, it's like x equals negative 2. Well, that's the x coordinate of the point of intersection. Looks like the y coordinate of the point of intersection would be 3. But notice how we don't even need to figure that out, right? Multiple choice test. Just choose A. You're done. Yeah, interesting problem with 23. I mean, you're gonna have to have like decent game when it comes to finding the GCF of algebraic expressions featuring, x and y and variables and all that. So let's find out the greatest common factor of these two. So the greatest common factor is a number that goes into both numbers. So this is a number. This is a number. We need a factor that goes into both of these. And we want the greatest of common factors, okay? Now, x squared does not go into both of these because this doesn't have an x squared. It's got an x, but it doesn't have an x squared. But both of these definitely have an x in it. I mean, there's, x times y squared would give us this, and x times xy squared would give us that. Okay, so I'll say it again, x times xy squared would give us that. So x is most definitely a GCF. Okay, so we're going to sort of calculate the GCF. X is part of the GCF, but then you can kind of analyze the y. So notice you just do things like one at a time. Focus on the x's. You can realize, oh, x goes into this and x goes into that. And then as far as the y's go, I mean, we're looking at y squared, right? I mean, y squared goes into both of them clearly. So it's going to be y squared. That actually is the GCF of these two. I mean, there's no ifs, ands, or buts about it. That's it. That's the GCF. Now, apparently, the GCF is equal to 45, right? So it's like, okay. Apparently, this is true, according to the problem. And that means that there's some number times a perfect square, because y squared is a perfect square, equals 45. So once again, there is some number times a perfect square equals 45. That's the way to think about it. Well, what's one of the factors of 45 that's like a perfect square? Well, 9, right? Isn't 9 a perfect square? So in other words, we could think x times 9, 3 squared, equals 45. Okay? So y could be 3. Y could be 3. Okay, once again, we have some number times a perfect square gives us 45. The perfect square factor of 45 is 9. So what squared gives you 9? 3. So that's how you do that one. That is answer choice E. Yeah, 25 is certainly a unique problem. Just another example of like the sort of unique problems you're going to have to deal with on standardized tests that you don't often get in school. So the bottom line is we've got a caution sign that flashes every 4 seconds. So, imagine the star represents a flash, and then it's 4 seconds, right? And then there's another flash, and then it's 4 seconds, okay? And then there's another flash, and so on. So you can imagine that going on for a while, right? And then as far as the other one, it's like there's a flash, there's that moment where they flash together, but then it's like 10 seconds, right? And then there's a flash and so on. And then it'll be another 10 seconds. So we'll represent that. I mean, that's one way of visually representing what's happening here. Um, I'll just cut to the chase. I mean, the key with solving something like that would be to find the least common multiple. Because if you think about it, let's just think about this right now. The least common multiple of 10 and 4, that's actually 20, right? And let's look at what's happening. I mean, 20 seconds is already represented here, right? Before there's another flash. We'll do this flash over here, okay? 20 seconds is already represented. So let's analyze what happens here. I mean, we would have another flash. That's a star. Terrible looking star. 4 seconds would go by again, and there'd be yet another flash, right? And then finally, another 4 seconds would go by, and there's another flash. And by that time, 20 seconds has elapsed. 20 seconds has elapsed down here. So this represents like the first moment where they flashed at the same time, and then this guy flashes a lot. This one flashes once more, kind of in between. But then they both flash again right there. Okay, they both flash right there. So the key with something like that, where you have this, I don't know what would the word be? Uh, Synchronistic flashing of lights, or I don't know, trains running by each other at a certain time or something. When you have this synchronization happening, just ask yourself, would it be helpful to find the least common multiple to find out where they jive again? And then they're going to do it again 20 seconds later, right? So LCM, that is answer choice D. Number 26 is very abstract. This could be an example of the kind of problem where you might want to just like plug in your own numbers and do a little bit of trial and error where you test different values for A and different values for B. Now, unfortunately, what we're going to do is we're going to take the time to kind of go through each um, answer choice, right? So according to um, F is suggesting that that's always negative, right? But it's like, no, right? I mean, A could be 300 and B could be 1, right? In which case this would be 299. Clearly, that is not negative. I mean, clearly, right? So that's gone. Answer choice G. Answer choice G. That is, I'll just fill that in, negative A minus B. Well, we could have, um, it's all non-zero values of A and B. I mean, clearly we could have like something like negative 10 minus, and maybe what if B was like negative 20 or something, right? Then it would be negative 10 minus negative 20, meaning negative 10 plus 20, which is 10, right? So that's gone, right? We just we just provided a counterexample where it's conceivable that negative A minus B could end up being positive, actually, all right, despite the appearance of it. Um, Assuming that A and B could be any non-zero value, which according to problem number 26, that's true. It says for all non-zero values of A and B. So I'll just tell you, H and J, you could plug in numbers and discover that there's no reason to believe that H and J would always be negative. But let's look at K. Now, K is the answer, but let's look at Y. Okay, so according to K, we have this. Okay, so this is going to be a negative positive number, which means that no matter what, absolute value is always positive, but it's a negative of an absolute value. So it's like, imagine you had the absolute value of whatever, and it's like positive, but then it's like negative on the outside. So that's just definitely going to be negative. It's like negative, like unavoidably negative, this first term. Okay. And then it's going to be subtracting a positive number, right? It's going to be subtracting a positive number. It's not subtracting a negative number. Think about a negative number, like negative 1, subtracting a negative number. Well, that turns out to just be adding, doesn't it? Right? So when you subtract a negative number, it turns out to just be adding. But when you subtract a positive number, that's just subtraction, right? I mean, imagine negative 1 minus positive 3. Well, that's just negative 1 minus 3. And you know what that does? It brings you further down the number line into the negative region. And, brings you to negative 4, in fact, right? Which is further to the left of the number line than where we started. So when you have a negative number, minus a positive number, of which absolute value b is, you're just going to get more negative, more negative. In the same way that you started with -1, you subtracted a positive number, and you ended up more negative with that -4. So that's sort of one way of understanding what's going on there. I think as long as it clicks conceptually, the chances of you being fooled by a problem like that again, drastically low, because you'll start to think in these terms of, you know, this would always turn out to be negative. This whole thing, you'd be subtracting a positive number. What happens when you have a negative number subtracting a positive number? Oh, you get even more negative. So there's just no way this result could be positive. So K is the answer. So problem number 39 features a trigonometric function that is such that a lot of students really just don't have a lot of familiarity with this kind of stuff. Now, very quickly, I just want to say that the parent function of the function that they gave you, like the normal version of it, is that. And the way to graph that, it's kind of like a vase that goes like that. Now, it is actually the case that it goes forever. Okay, this cosine function, it actually goes forever, but usually when textbooks will present the graph of this parent function, it goes down like that and then up, and this is called a period. This is the most famous like period that they sort of highlight. It's like this vase shape now. Bottom line is the y value you could say is 1. The y value there is -1, and that pertains to the parent function. It's also the case that this x value is typically denoted with 2 pi for 2 pi radians. Therefore, the middle point there would be pi. It's also the case that this is pi over 2 and this is 3 pi over 2. We're not going to worry about that for now. The amplitude of a function like this, a trigonometric function like cosine x or even sine x, which is sort of a different looking graph, the amplitude is the absolute value distance from the center region up to the maximum or down to the minimum. So it's the absolute value distance from the central oscillation, point down to the minimum or up to the maximum. Now, another way of saying it, some books, including some ACT practice tests, will say, oh, it's half the distance. It's half the distance of the max and min. So if you took the max, which is 1, and you subtracted -1, well, 1 minus -1, 1 minus -1 is 2, so half of that is 1, so therefore the amplitude of this is 1. And the amplitude, by the way, is given by the number that's like right in front of cosine x. It's that invisible 1 that's right in front of cosine x that tells you that from the center line it goes up to the maximum. From the center line it goes down 1 to the minimum. It's only a unit, 1 unit down. Anyway, I'm kind of repeating myself. Now, how does this apply to our problem? Our problem says, okay, f of x equals 1/2 cosine 3x plus pi. So it turns out, like I said, the amplitude is to be found here, right? Well, what's the amplitude then? It's 1/2. Look how easy that is. Look how easy that is. That means that this graph, this cosine graph, I understand you're probably wondering what's going on here. This has to do with horizontal shifts and period changes and things like that. We're not going to worry about that. But basically, that means that this cosine graph, as it goes up and down and up and down and up and down forever, it never gets higher than 1/2. And it never gets lower than -1/2. You know, the peak of the mountain is 1/2. The valley gets only as deep as -1/2. That's what the amplitude means. So the answer to this one is B. So problem number 47, I mean, most people when looking at it, they would see, oh, well, there's probably a way to cancel something out from the top and the bottom and all that stuff. And they would be right because um, this is a rational, well, rational expression, let's just call it that. And we got 3x squared down there. So it's most definitely the case that there's a GCF that can be factored out of the top right there. So we're going to sort of analyze that right now. Now, when you're trying to figure out like the GCF of two terms like this that are sort of complicated, I mean, there's a lot of stuff going on, you might want to focus on the numbers first instead of like thinking about the variables just yet. I mean, you don't want to do too much at once. So it's like, what is the GCF of just 12 and -9? I mean, GCF of that is 3, right? So you just put a 3 there because you know you're going to write a 3, right? I mean, the GCF, you're going to factor it out. So there's your 3. Now let's focus on x to the 6 and x squared. So if you're dealing with like x to the some exponent and x to another exponent, the GCF is always going to be the x to the smaller exponents because x squared times 1 gives me x squared. X squared times x to the 4th gives me x to the 6th. So clearly the GCF is x squared itself, okay? So if you didn't follow that, just remember when it comes to the GCF of x to the some exponent and x to another exponent, it's going to be the one that has the smaller exponent. That's going to be the GCF. So we're going to factor that out, x squared. And then it's going to be parentheses, because I know I'm going to write that. I know I'm going to write parentheses here. Uh, and I'm going to put stuff in there. Now, I'm a big fan of just writing the parentheses because you're not going to write that anyway. And it's going to be all over 3x squared. Now, already we can see, I mean, it's going to be amazing because these are going to cancel, right? So I'll just leave that there in the canceled form because we know we're going to do that. So really, it looks like the answer is going to be whatever the heck is inside the parentheses. Now, this could be confusing. Maybe just work with the numbers. It's like 3 times what gives me 12? Well, 3 times 4. So just put a 4 because you know that that's going to be part of the first term. And then you could ask yourself, okay, x squared times what gives me x to the 6th? Well, that would be x to the 4th. And then 3 times what gives me a -9? Well, that would be a -3. And then you could ask yourself, x squared times what gives me x squared? Well, that would be a 1. Now, I do not have to write that 1 because 1 times -3 is just -3, so we're going to leave it alone. And looks like this just turns into, I'll keep it in blue, 4x to the 4th minus 3. And that is answer choice E, it looks like. And that is correct, E. Problem number 49 turns out to be easier than it looks once you know how to transform parabolas. So the parent function of a parabola is as follows. Let's call it f of x equals x squared. So really all you need to know is the following information where the parent function is just a regular parabola that looks like this, and it goes on forever like that. And at a certain point in time, you either have or you will learn that you can apply various transformations to this. For example, you could say x squared plus 2, in which case it would shift everything up by 2 units. You could say x squared minus 2, in which case it would shift everything downward 2 units. But one of the famous transformations that you can apply to the parent function is to stick a number other than 1, because right now there's a 1 times x squared. You could stick a number other than 1 in front of the x squared. Let's try something like 3x squared. So now we have 3 times x squared. So basically, this would be the parent function. The red one would be the green one, except we have this 3 in front. So what does that do? Well, basically what that does is stretch all the heights of the points composing the green parabola. It stretches those heights upward by a factor of 3. Okay. So what do I mean by that? Well, you can imagine there's an xy coordinate to this point here. Let's just focus on this point here. Well, when you multiply x squared by 3, what it does is it takes the height that it used to be, the y coordinate that this point used to be, and multiplies that y coordinate by 3. So now the height of that point is 3 times what it used to be. Okay, so we could say the y coordinate, also known as the height of that point, is now 3 times what it used to be. So it's this stretching upward moment. Notice how in the green parabola, the y coordinate of the vertex is 0. So when you multiply 0 times 3, that just remains 0. And that's one reason why this red parabola remains situated at the vertex. Uh, it's interesting to kind of note that, yeah, it's being stretched upward, but it most definitely gives the appearance of being narrower as well. So the green seems to have narrowed. I don't really like that description. I prefer thinking of the green parabola as having been stretched upward. Okay, so that is what this number does. It is a vertical stretch. Now, some of you might be thinking, what about if you did something like this? What if you stuck fraction in there? Well, the fraction would do the same thing in a sense that it would be 1/2 times the height. Before it was 3 times the y coordinates of each point, but now it's going to be 1/2 times the y coordinates of all the points in the parent function. So this would give the appearance of smushing the green parabola down like that, where once again, let's focus on the parent function. Imagine this point right here. Well, it used to have a y coordinate of, a certain amount, that height, but now that height has been diminished by half. Okay, so now the height of this point right here is half of what it used to be. So basically, it's smushing the parabola down. So that's what a fractional coefficient will do to the parabola. Now, again, some teachers and some people might talk about how it gives the appearance of the parabola being wider, and that's most definitely true. But again, in my opinion, it's more helpful to think of this green parabola as having been smushed downward. Okay, all the points have been smushed downward. So that is what the coefficient in front of the x squared does to a parabola. Now, I do want to just make a mental note. There's another thing, I'll call this ix. There's another thing that the coefficient denotes when it comes to the graph of a parabola, and that is that if it's negative, for example, if it was something like negative 2x squared, well, the fact that there's a 2 means the x squared, means the parabola would most definitely be vertically stretched. But the fact that it's a negative means that it would also be reflected across the x-axis. So basically, you can imagine the green parabola, which corresponds with the parent function, being reflected across the x-axis and being stretched at the same time. So that would give the appearance of something of a narrow looking upside down parabola. Okay, so when it comes to problem number 49, it turns out that really these are the only aspects of transformations that you need to know to solve the problem. So when you look closely at the parabolas, what you see is um, the bottom parabola, which is sort of the widest parabola, is associated with n equals 1. The medium one, which is certainly narrower, also known as stretched upward, has an association with n equals 2. And finally, the most narrow parabola, also known as the most stretched upward parabola, is associated with n equals 3. So clearly we could see that as n increases, this parabola gets stretched upward. Well, that corresponds most definitely with sort of the relationship certainly between these two, where you had a parabola, but then the coefficient just increased, n just increased. So clearly n must be the number that's in front of x squared, and that is why a is the answer. Okay, let's look at d and e. Now d and e have a negative n, or we could say a negative coefficient in front of the x squared, and that would result in a reflection across the x-axis. So those are easy to get rid of. Answer choice C has an n that's being added to x squared. Well, that's a vertical shift upward. That's not a vertical stretch. Okay, that's a vertical shift upward. So that's not a vertical stretch. Um, Answer choice B would suggest that as n increases, the fraction would become less and less. Because if you think about 1 over n, think about 1 over 2. Well, that's 1/2. And then let's make n a little bigger, so n becomes 3. So that would be 1/3, right? And if you notice, 1/3 is actually less than 1/2. So answer choice B is wrong for that reason. As n increases, the parabola denoted by answer choice B would actually get more and more smushed. So I'll say that again. As n increases for answer choice B, as the denominator of that coefficient increases, the fraction would actually get smaller if you think about it, because 1/2 is greater than 1/3, which is greater than 1/4, and so on. So answer choice A is the only one that makes sense for all of the previously mentioned reasons. So for problem number 49, we are looking at A. So problem number 52 is a somewhat tricky algebra problem that features a lot of substitution. So I can already tell I'm going to need room. So let's set up the first equation based off of the first sentence. Lucky found $8.25 in pennies, nickels, dimes, and quarters while walking home from school in 1 week. So already that um, you know, information could be represented as the following equation. First of all, let's make sure that we know that the following is true. So we're going to say that P represents the amount of pennies Lucky has, N represents the amount of nickels Lucky has, and D represents the amount of dimes Lucky has, and Q represents the amount of quarters Lucky has. And we're just going to kind of set that information off to the side and set up the equation that I was talking about. And basically the equation is it's going to be, let's actually put $8.25 just in terms of cents. So hopefully everyone understands that $8.25, that really equals literally 825 cents. Now, what I'm going to do is I'm going to avoid using decimals in this problem because to me, decimals can be confusing. And just put everything in terms of actual cents. Okay. And we're allowed to do that. I mean, essentially, we would just be multiplying everything by 100, and therefore we're dealing with 825 cents. So the bottom line is, as far as the special equation that we could write, it would be that 1 cent times P, which is 1 cent times the amount of pennies Lucky has, plus 5 cents times the amount of nickels Lucky has, plus 10 cents times the amount of dimes Lucky has, plus 25 cents times the amount of quarters That's all going to equal 825 cents. Okay, also known as $8.25. So that's something to, definitely consider right out the gate. Then the problem gives you all of this sort of additional information that can be really, really confusing. So I'm just going to show you how I work through this kind of stuff in my head. You just take one statement at a time and just be super careful, just be super meticulous with it. So, for example, when she deposited this money in the bank, she noticed she had twice as many nickels as pennies. So already the problem is mentioning a relationship between nickels and pennies. So what I'm going to do is I'm just going to write an N and I'm just going to write a P. And I know that there's some relationship there, so I'm going to write an equal sign. Then I pause and just think about it. Twice as many nickels as pennies, which means that there's more nickels here, which means that that has to be 2, okay? So you have to be super meticulous with that. N equals 2 times the amount of pennies, okay? So if it says that Lucky has twice the amount of nickels as pennies, that means N equals 2p, okay? The next statement says she noticed she had twice as many nickels as pennies. I already said that. One fewer dime than nickel. So apparently there's a relationship between dimes and nickels as well. So we're going to write D and we're going to write N because I know that there's a relationship between the two. I'm going to write a little equal sign and we're going to think about it. One fewer dime than nickels. So that means there's less dimes than nickels. In fact, there's one fewer. So it's going to be N minus 1. Okay, so you have the amount of nickels, and then if you were to subtract 1, well, that's how many dimes you have. Okay, so that's that. And then finally, they say one more quarter than nickels. So once again, I'm just going to write Q. I'm going to write N. I'm going to put an equal in between them and then just look at it. So it says one more quarter than nickels. So that means Q equals N plus 1. Okay, you have a certain amount of nickels, and if you were to add one more to that, well, that's how many quarters you have. Okay, so that's how you navigate those equations, and those are very important equations. The final question is, how many quarters did Lucky find that week? So the key to solving this problem is to refer to the above equation that we constructed, and we want to solve for Q, which means we have to change each of these variables, D, N, and P, in terms of Q. Okay, we need to figure out what D is in terms of Q. We have to figure out what N is in terms of Q. We have to find out what P is in terms of Q. And once we get, once we do that, then we can just, solve for Q. So that's a tricky one, right? Well, one thing we can immediately see out the gate is that we can totally find out what N is in terms of Q by subtracting 1 from both sides. So imagine we did that. We would end up realizing that really N equals Q minus 1. That's an equation that we could definitely work with. Okay, I'm going to do little dividers here because we really have like 3 equations here. We're going to work with each one. But as it pertains to this first Q equals N plus 1, we could turn it into that, and therefore we know that N equals Q minus 1. So what that means is anytime I see an N, I can replace it with a Q minus 1. So let's actually do that over here because we want to find out what dimes are in terms of quarters as well. So if we replaced N with Q minus 1, then we could easily see what dimes are in terms of quarters. So let's go ahead and replace this N with Q minus 1. So I just did that. I just replaced N with Q minus 1, and then I actually simplified it. So D actually equals Q minus 2, and I think we should wrap that in a yellow rectangle just to draw attention to it because we're going to be using that. So now we know that N equals Q minus 1. We know that D equals Q minus 2. Well, what about this one? Well, the key to sort of figuring out what P is in terms of Q is simply to replace this N with Q minus 1 because we already know that N equals Q minus 1. So we're going to do that right now. So I did that, but let's look at this real quick. I replaced n with q minus 1, but then we want to solve for p, so I divided both sides by 2, and we end up with p equals q minus 1 over 2, and then I wrapped that yellow box around it. So we're going to use all the equations that are in the yellow box and bring them into this problem. So let's start with p. P we know is equal to q minus 1 over 2, so we could just simply write that. And then we're going to be adding 5 times n. So it's going to be plus 5 times, well, what is n? N is q minus 1. So we must put that in parentheses, q minus 1. And then it's going to be plus 10 times d. So it's going to be plus 10 times whatever d is in terms of q. Well, we already discovered that d equals q minus 2. So we're going to write q minus 2. And then after that, we just have plus 25q. So what's great is that you don't even have to write anything here except 25q because it already has a q in there. So we're actually good there. And that equals 825 cents to be specific. Now, we have an annoying denominator of 2 happening right now, and I don't like it. So I want to get rid of it. I'm going to get rid of that annoying denominator of 2. And the way that I'm going to do that is multiply literally both sides of the equation by 2. Okay? And you're going to see why in a moment. But let's focus on the right-hand side because that one's kind of easy. That's going to turn into 1650. Okay, now let's analyze what happens over here. That's going to distribute there, 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 and there. Okay, the 2 is going to distribute to all of these places. So let's analyze what happens each time. When 2 gets distributed to this one, the 2's are going to cancel, and it's just going to leave us with q minus 1. When the 2 distributes here, you want to be careful. 2 only multiplies to that 5. You have to be super careful. You don't want to go 2 times 5 and that thing. You pick one of these two numbers. You have two numbers. You have 5 and you have q minus 1. Q minus 1 is just a number. It's a quantity. You just pick one of those two to multiply 2 to. And in this case, it's going to be easier for us to multiply 2 to 5. And then we have to actually preserve q minus 1. So you do have to be careful with that. 2 times 5 times the quantity of q minus 1 is going to turn out to be plus 10 times that quantity. Notice how q minus 1 is preserved. Now we have 2 times 10 times the quantity of q minus 2. Well, that's going to be plus 20 q minus 2. And then we're going to have 2 times 25q, and that's very clearly 50q. So we have q minus 1 plus 10 times q minus 1 plus 20 times q minus 2 plus 50q equals 1650. Now that is a lot of information. It could be a little confusing, but at least now we only have one variable, and it's the variable that we want to solve for. It's the variable that 52 is asking about, problem number 52. So that certainly means that we're on the right track. Now at this point, there's not much we could do to simplify this, but let's distribute the 10 into this quantity. Let's distribute the 20 into this quantity because that's what PEMDAS says we should do. Before we add any of this stuff or combine like terms, if there's an opportunity to multiply something, we're going to want to do that. We do have an opportunity to multiply something. We could distribute the 10 here. We could distribute the 20 there. So I'm just going to sort of rewrite this equation where it's q minus 1 plus 10q minus 10 after distributing plus 20q minus 40 plus 50q, and that's going to equal 1650. I like to draw attention to the like terms. So for example, I'm going to put a blue underline under all the terms that have q in it. That way I can very easily combine those. So let's look at that. Q plus 10q is going to be 11q, plus 20q is going to be 31q, plus 50q is going to be 81q. 81q. Now, all the terms that don't have an underline underneath it, I'm going to combine those. So we have -1 plus -10 is -11 plus -40 is -51. So it's just going to be 81Q minus 51, and that's going to equal 1650. So at this point, of course, we're going to have to add 51 to both sides. I'll denote that right now. And what we have as a result is 81Q equals 1650 plus 51. Now that is 1701. All right, now I know that that's 1701, but I like to just say it like that's easier on my brain to just say the numbers. So at this point, as many of you at home know, you would have to divide both sides by 81. And then, believe it or not, you are going to have the answer. The answer is, that's an arrow, the answer is Q equals 21. And that is answer choice J. So that's how you do problem number 52. So problem number 53 relies on you remembering that anything raised to the 0 power equals 1. So if they say something like the following, if they say something like 10 raised to the 2x minus 1 over x, and that equals 1, well then this exponent has to be 0, because the only exponent that you could raise 10 to and get a result of 1 is the exponent of 0. So what's kind of cool about this is you could just forget about the 10 and you could forget about the 1 and just work with this exponent. I mean, the bottom line is we know that 2x minus 1 all over x equals 0. Now, I'll kind of throw a little bit of fancy reasoning at you guys right now, because basically, um, first of all, we know that x cannot be 0. Okay, so that's, certainly true of this problem, because if x was 0, then it would be undefined. So we have to assume that x is some number other than 0. Okay, we have to assume that it's some number other than 0. And have you noticed that, like, let's say you have a denominator of 3, anytime you have a 0 in the numerator, well, that equals 0. And this is just an example, right? Anytime you have a numerator of 0, it turns into 0. Okay, as long as the denominator is not 0 and therefore undefined. So you could have any numerator down here. It doesn't even matter what the numerator is, or the denominator rather. You could have any denominator down here. It doesn't even matter what the denominator is. As long as that numerator is 0, well, the whole thing's equal to 0. In fact, that's the only way that this fraction could be equal to 0. Okay, so therefore, in a way, we could just simplify this equation, the green equation, even more by not even worrying about that denominator and just sticking the numerator equal to 0. Okay, now some of you might be noticing, well, we could have also multiplied both sides by x and it would have turned into 0. So that's true. So solving this equation very simply would give us, let's see, adding 1 to both sides would give us 2x equals 1, and dividing both sides by 2 would give us x equals 1/2. And that is the answer. It is C. So problem number 55 requires you to understand a lot of different concepts, unfortunately. For example, you're going to need to know that the rate times time equals distance if you're ever dealing with like an average speed problem or whatever, or really just most problems that feature speed and distance. That's going to come into play in this particular problem. Also, it's helpful to know that, well, it's crucial really to know that the um, circumference of a circle is 2 pi times the radius. Some people like to think of that as pi times the diameter as well. And that's actually a good way of thinking about it, because 2 times r is the diameter, so it makes sense. It's going to be the diameter times pi. We're actually going to use this definition in this problem here. So just to kind of refamiliarize yourself with that. Another thing worth noting as well is the following phenomenon that really, as far as I could tell, does not get discussed that much in geometry class. And that is the following. We're going to put this here for reference. If you have a wheel and you have a certain circumference, let's say the circumference of the wheel is 10 inches. Okay, now this has nothing to do with the actual problem as far as the numbers, but the concept definitely applies. So imagine the circumference is 10 inches, meaning it goes 10 inches all the way around. Well, if you do a full revolution of the wheel, if you do a full revolution of the wheel and you end up here, and it's just a single revolution, well, you have just traveled 10 inches, okay? 10 inches. So, in other words, the distance traveled by a full revolution of a wheel, one full revolution, is the circumference of the wheel. So I'll say that again. The distance traveled by one full revolution of a wheel is the circumference of the wheel. So as you can see, it went 10 inches and the circumference is 10 inches. Now that's just one full revolution. Now, if there's 200 of these revolutions, well, this wheel is going to travel 200 times 10, and therefore it would travel 2,000 inches. Okay, so that's important to understand. And it turns out that in this problem, you're also going to have to be fairly skilled when it comes to unit conversion, which we're going to get to soon. Okay, so in my opinion, that's what makes this a difficult problem, is because you have all these concepts packed into a single problem. You have circumference, you have rate times time equals distance. You need the insight that one full revolution, the distance traveled by one full revolution of a wheel, is equal to the circumference of the wheel. You're also going to need to be skilled with unit conversion. So that's already like 4 things in there. Okay, now we're going to leave these here for just reference for now. So at the end of the day, we want to know at what average speed in feet per second was Mario riding during that minute. Many of you can see that one of the issues is that we don't have feet per second. I mean, we have minutes and we have inches. I mean, the problem provides us with inches and minutes. Um, so seeing as how the final question nonetheless is asking about average speed in feet per second. Well, it's like, okay, we don't have feet per second, but let's find the average speed in um, as it pertains to inches and minutes. Okay, let's just start there. If we could find the average speed of inches per minute, then we can start to think about the average speed in feet per second by doing a unit conversion. So once again, the plan is to just find the speed for Mario's bicycle riding in inches per minute, because that's what they give us, and then we'll convert it later. So how can you find Mario's speed in inches per minute? Well, the speed is r, okay? And the time that he traveled was 1 minute, okay? So I'm just going to write 1 minute, all right? Just write 1 min. But what is the distance that he traveled? What is the distance he traveled? Well, the distance he traveled was 200 revolutions. But what is that distance? 200 revolutions. Well, do you remember how I said that there's an interesting relation between the circumference of a wheel and how far it travels in terms of distance? Well, that's going to be the case with this problem, where we will indeed find the circumference of Mario's wheel based off of the diameter that they give us. Now, apparently, the diameter of the wheel is 26 inches. Okay, 26 inches. And as I had mentioned before, the circumference is equal to pi times the diameter. So we will then say that the circumference of Mario's wheel, C sub m, is going to be 26 inches times pi. So in reality, it's 26 pi inches. Okay, 26 pi inches. So that's the circumference of his wheel. Now, we also know that he traveled 200 revolutions. Okay. Now, do you remember how I said that the distance traveled by one revolution is equal to the circumference? So if he was to travel one revolution with the wheel, then he would have traveled 26 pi inches. But he didn't travel one revolution. He traveled 200 of those. So the distance traveled will be 200 times the circumference of his wheel. So I'm actually going to go ahead and write that immediately in this equation. So the distance, right, is going to go right here. And that is going to be 200 times the circumference, which is 26 pi inches. Okay. And that's going to be huge. Okay. Because now we can find at least the speed, also known as the rate. We can find the rate at least in inches per minute, and then we'll just convert that to feet per second later, and then we'll have our answer. Okay, so we're finding the speed of inches per minute. Well, in order to do that, we have to solve for r, which means get r by itself, and obviously that's going to be a matter of dividing both sides by this 1 minute thing right here. 1 minute. And that, of course, would cancel these. And then we would have r equals, let's kind of work this out right now. 200 times 26 pi, that's going to be 5,200 pi. 5,200 pi. So again, 200 times 26 pi, hopefully I said that correctly. 200 times 26 pi is 5,200 pi, and that's inches on top. So I'm going to write, I'll just write IN for inches, all over 1 minute. Okay, so we know that the rate that he's traveling, the speed, is literally 5,200 pi inches per minute. That's the speed. So then now you might be wondering, okay, well, how do we convert this speed into feet per second? I'm a big fan of using this sort of grid system when doing unit conversions. It's a beautiful way to just keep the information organized. So you just draw a couple of these. It might be too much. I mean, we'll see. It might be too much, but let's just be very clear. This person travels, 5,200 pi inches per minute. So I'm going to write 5,200 pi, and we're going to have the word inch here over 1 with the word minute, okay? Now, when it comes to unit conversion, writing not only the numbers, but also the words are really important. So we have inches and minutes. So the presence of the words is crucial, okay? So from there, we need to realize, well, in the final answer, we don't want the word minute and we don't want the word inches in there, right? So we have to set things up across this whole thing in such a way that would enable us to cancel these words. Not necessarily the numbers, but we want to cancel these words out. And this is something that over time can even become fun once you get the hang of it. Okay, there's something satisfying about it actually. At the end of the day, our goal is to get rid of inches and minutes and to replace them with feet and seconds. Okay, so what we need to do is brainstorm, well, what are some of the relationships between minutes and feet and seconds and inches and feet and seconds? Well, right away, you can see that there's certainly a relationship between minutes and seconds. So what we're going to do now is just force the word minute to be up here. And the reason for that is because I'm going to want to cancel these. So you have to do, when you do these cancellations, they have to be diagonal from each other in order to cancel them. So I definitely can foresee that there is a relationship between minutes and seconds. I want to cancel the word minutes, not necessarily a number, but the word itself. So I'm going to put the word minute in that diagonal position right there. And then I ask myself, okay, well, what is the relationship between minutes and seconds? Well, obviously, there is 1 minute corresponding with every 60 seconds. So I'm going to write SEC for that, okay? Now, I am going to cancel the word minutes, but not yet. Let's fill out the rest of the table first. We know that they will cancel though, for sure. We also want the word feet in there, not inches, so we got to find a way to cancel inches out. Clearly, there's a relationship between feet and inches, so I am prepared right now to immediately put the word inches down here, and I'm just going to do IN. And just remind myself, well, most definitely 12 inches correspond with every 1 single foot. Now, what I've done is I have set the table up in such a way that the words that I want to cancel will cancel, and the words that I want to remain will remain. And let's see what that looks like actually. So that would look like this word inch crossing out or canceling with this word inch. Notice how I'm not canceling the numbers. I'm only canceling the words. And it would also be the case that the word minute would cancel with that word minute. So at this point, we've done the cancellation process where the word inches have been canceled and the word minute, the words minutes or whatever, have been canceled, okay? And now only the word feet and second remain. That's progress. At this point, all you have to do is multiply straight across. So when we multiply straight across, I'll actually get rid of this part. We don't really need that part. Once we multiply straight across, it's going to be a fraction, right? It's going to be a fraction. It's going to be 5,200 times 1 times 1, 5,200 pi, I should say. So that's 5,200 pi all over 1 times 60 times 12. Well, that is 720. Now, what you might want to do is just work with the numbers first, set up a nice fraction, okay? And then bring these sort of words in off to the side, the remaining words. I will put feet in green over seconds in blue because the word feet in the table was green and the word seconds was blue. So in a way, this is the answer, 5,200 pi over 720 feet per second. That's the answer. However, obviously that does not show up. Well, the good news is that 5,200 pi over 720 can be reduced to 65 over 9, okay? Now, let me just rewrite that as 65 pi over 9 feet per second, okay? Now, some of you might be wondering, okay, well, the pi is on top, but in answer choice A, the pi is off to the side. Well, that is actually okay. All right, let's just be very clear. So the answer, by the way, is A, in case you haven't noticed. Let's be very clear that this is equal to 65 over 9 with a pi hanging off to the side, okay? Because the reality is there's secretly a 1 underneath that pi. So it's really 65 over 9 times pi over 1. Okay, so I'll say that again. It's really 65 over 9 times pi over 1. And another way of representing that is this, 65 over 9 times pi over 1, because, every number has secretly a 1 underneath. So if you have multiplication in the numerator, just know that one of those numbers that's being multiplied on top could be sort of represented as hanging off to the side like that. And just to be thorough, I'll also continue to write feet per second. Okay. Now, let's be very clear though, this is the number. Okay. It's this amount of feet per second. Okay. So that is how you do that one. Okay. So again, I want to make clear 65 pi feet per 9 seconds is the same thing as 65 over 9 pi feet per second. All right. So just take a look at this, and just realize that these are actually saying the same thing. And the final answer is 65 over 9 pi, which is answer choice A. Problem number 57 is deceptively easy because the truth of the matter is if you have an arithmetic sequence, for example, let's say the first term is 3, let's say the next term is 5, so everything goes up by 2. Let's imagine that. 9 and then 11. And let's say we have, 5 terms or what have you. Well, clearly the median would be the middle number. It would be 7. Now, I'll just tell you right now, I mean, when it comes to arithmetic sequences, the mean, or the median rather, will always actually equal the mean. Okay, that's not true for any list of numbers, but it's definitely true for an arithmetic sequence. So the median and the mean will always be the same if it's the case that these numbers are spaced apart, by the same amount of units, also known as an arithmetic sequence. Okay, so therefore, the answer to problem number 57 is A, because they already tell us that there is a finite arithmetic sequence. It's got 7 terms. They give you this extra information of saying, oh, the first term is 3/4, and they want to know what's the difference between the mean and median. Well, the mean and median are the same because it's an arithmetic sequence. So since the mean and median are the same, the difference between them is 0 because any number minus itself will be 0. Now, I understand that some of you might be wondering, what if it wasn't like a weird trick question like that? What if it was like a real problem? And some of you might not be wondering that. Okay, some of you might be happy that, oh, okay, that's the answer, moving on. So for those of you who want to move on, I totally invite you to do so. But since we're on the topic, for those of you who would like to maybe have a quick sample problem when it comes to arithmetic sequences, I'm just going to throw one in there for you right now. Okay, let's imagine we have 7 numbers and they are all numbers in an arithmetic sequence. So that is 5, 6, 7. Let's say that the first number is 70, and we will say that the last number is, let's get a little crazy, the last number is 950, okay? And what they want to know is, what is the median of these 7 numbers, okay? What is the median of these 7 numbers? So how could you go about that in a way that would be systematic, well organized, and efficient? That's the question. Well, the way to go about arithmetic sequence problems is to use this formula that says a sub n equals a sub 1 plus n minus 1 times d. Okay, now let's be very clear. Let's actually start here. A sub 1 is the first term. Okay, so in this case, it would be 70. All right, let's make clear that that's definitely a 0 right there. So a sub 1 would be 70. D is the space in between each number. So if the next term in the sequence is 74, well, the difference between this term and that term is 4, and therefore D is 4, okay? And that's actually the feature of an arithmetic sequence. An arithmetic sequence is a list of numbers that go up by the same amount each time, or go down by the same amount each time. One way or the other, you're adding the same number to each successive term to get to the next term. So D represents that number. Now we don't know what D is here just yet, okay? We do know that a sub 1 is 70. So that leads to the question of, well, what about n? We have an n over here, we have an n over there. What does n mean? Well, let's focus actually here. A sub n, what that means is the nth term. So for example, this is the fourth term. So this is called a sub 4. So if we want to find the fourth term, which by the way we do, you would write a sub 4 equals a sub 1 plus 4 minus 1d, okay? Now, I actually think we should go ahead and flesh this out because at the end of the day, isn't that what we're trying to find? We're trying to find a sub 4. So I'm going to write a sub 4 equals 70 because that's a sub 1 plus 4. We'll put 4 in blue right now just to kind of color code things. 4 minus 1, and it's still times d. So obviously this is going to become 3, but this is the equation that would allow us to find a sub 4, also known as this fourth term. This is the equation. So we can clearly see that the roadblock is that we don't have d. So we have to go on a separate mission called find d. Figure out what d is, okay? Because if we had d, it'd be easy. It'd be 70 plus 3 times d, and then we'd have our answer, literally, because that's what we're trying to find. In fact, I'm going to put a question mark right there. That's what we're trying to find, a sub 4. So the question is, well, how do you find d? Well, what you could do is you could actually use the same equation, but plug in pieces of information that have already been given. So for example, we have things like the first term, and we have this term here. Now, what term is this? This is 1, 2, 3, 4, 5, 6, 7. So that's the seventh term, also known as a sub 7. Now, what we're going to do here is we're going to work with this term. A sub 7 turns out to be literally 950. Okay? We also know that a sub 7 equals a sub 1 plus n minus 1d, but we already have a sub 1. It's 70 plus n minus 1. So the 7, I'll write in blue down there. It's going to be 7 minus 1 times d. Okay? So really a sub 7 equals 950, and that also equals 70 plus 7 minus 1d. So what we could do is just sort of, ignore this part and recognize that 950 equals 70 plus 7 minus 1 times d. And therefore, we can solve for d. So on the next line, it would be 950 equals 70 plus 6 times d. And 950 minus 70 is 880. So 880 equals 6 times d. And then we would have to divide both sides by 6 to get d equals 440 divided by 3, or over 3. So that is a terrible looking number, but that's what you get sometimes when you make up problems on the fly like this. You're going to end up with weird numbers, but this could be a decimal, but we're going to leave it in this improper fraction form. So one way or the other, we have our d, which is great. And I'm actually seeing a cool cancellation that's going to occur. So we have a sub 4 equals 70 plus, let's just get this over with, because ultimately our goal is to find a sub 4, right? Now we have d, so that's all we needed. So a sub 4 equals 70 plus, that's going to be 3 times d, right? So it's plus 3 times whatever d is. Well, we have d. It's right here. That's d right there. 440 over 3. And what do you know? The 3's cancel, which is great. So therefore, a sub 4 equals 70 plus 440. And that equals 510. Okay, so that is an example of an arithmetic sequence problem, and we just figured out what a sub 4 is. We knew that it was an arithmetic sequence. We knew the first term, we knew the last term. Turned out that's all the information we needed. Just the fact that it's an arithmetic sequence, we have the first term, we have the last term. Now this could have been any term here. Had we had a number for a sub 6, well then we would have gone through the motions over here only with a sub 6, and that would have been 6 minus 1 times d. So hopefully that makes sense. Anyway, the answer to problem number 57 on the ACT practice test is A, just to reiterate. Okay, so problem number 59 actually baits you into using that trig formula. Now that is an interesting trig formula, the whole 1/2 AB times sine C. That most definitely could be used. There's no question. Um, but I'm going to present to you a way to do this without that. So we want to find the area of the triangle, right? And here's the triangle. We know that that's 4. We know that that's 5. I don't even care about the dumb decimals. That's extra information too. The fact that they gave us the 4.0 and 5.0, totally extra information. I don't care about any of that. We also know that the entire base, if we're going to treat this as the base, is 8, right? We also know that this angle that is in there is 30, okay? Now, before I dive in, let's just set this off to the side and remember something. I want you to just temporarily forget this. Let's remember something though. There's a special right triangle called a 30, 60, 90. And this right triangle is always such that the short leg is some number, we'll call it A. The hypotenuse will always be twice that. We'll call that 2A. And this sort of longer leg will always, always, always be A radical 3. That's something that you should be familiar with on the ACT. You should also be familiar with 45, 45, 90 triangles. And in case you don't know what that is, just Google that. But this is called a 30, 60, 90 triangle, and that's a famous right triangle. Because if you know these relationships, then you don't even have to use the Pythagorean theorem. And let's keep in mind, A, which corresponds with the shorter leg, right? Not the hypotenuse, but the shorter leg. That's always going to be across from the 30-degree angle. And that makes sense because 30 degrees is the smaller angle. 60 is a little bigger. So 60 degrees is going to give birth in a way, or it's kind of a weird metaphor, but it's going to, I don't know. I like to think of it actually as a spotlight that's kind of shining on a wall. Like this is the flashlight over here. And the beam of light has an angle of 60 degrees, so it creates a larger spotlight on the wall. If that makes sense, or on the floor in this case. So we have A over here. So my point is that the short leg will always be across from the 30-degree angle. Now, how does that apply? Well, that applies because we have the base, and we know that if we want the area of the triangle, which by the way is what they're asking for, they're literally asking for the area. And then they're saying to the nearest 1 centimeter squared, like as though we have to round it or whatever. We're not going to have to round it because the bottom line is all you need to find the area of any triangle is to find the base and the height, multiply them together, and then multiply that by 1/2. Okay? Well, we have the base, don't we? It's 8. So the area of this triangle is going to be 1/2 times 8 times whatever the heck the height is. But what's the height? Well, the height is the imaginary line that would connect the top all the way to the bottom in such a way that would form 90 degrees. Now look at what we have. We have a 30, 60, 90 triangle. And in case you're not sure that that's 60, well, think about it. 30 plus 90 is 120. 180 minus those two, the sum of those two would give us 60. So we have 60 up there. This is a 30, 60, 30, 60, 90 triangle. And this right here is the short leg. In fact, I'm going to call it A because that's what I called it over here. Okay. Now, let's be clear. A is the height. Okay. But let's find A. Well, in a 30, 60, 90 triangle, A, the short leg, is 1/2 of the hypotenuse. So, I mean, you could think of the hypotenuse as 2 times A, but you could also think of A as 1/2 whatever this long number is, or this large number is, right? So A is 1/2 of that. So A is 2. Now keep in mind I could have called this H as well. A case could be made that maybe I should have called it H because it is the height. But I wanted to call it A to make it correspond with this A. Okay. Now, let's go to the next line, therefore, and realize that, okay, well, it's going to be the area is 1/2 times the base, which is 8, times the height, which is 2. And guess what? We're totally about to solve this one. This is going to be 1/2 times 8, which is 4 times 2, which is 8. So the area equals 8. And that is answer choice C. Now, some of you might be wondering, okay, if you're anything like me, actually, you're wondering, okay, great. So there was like a math hack that we could use to solve this problem. But what if we didn't have access to that trick? What if we had to use that terrible looking formula, 1/2 AB sine C? So I'll just tell you, for those of you who don't care and you're happy with that hack, then go ahead and move on and, leave this video now. But for those of you who are curious, okay, what would we have done had we needed to use that formula? Well, I'm going to go over that now. So let's be very clear. They gave us a triangle. I think we're clear about that. They gave us a triangle. That's 4. I'm not going to do the decimal stuff. That's 5. That's 8 and 30 degrees. Okay. And then they basically say, oh, by the way, one way of finding the area of a triangle is you could totally just be like area equals 1/2 A times B times sine C. Okay. And then they kind of give you this gobbledygook, like explaining what A, B, and C are and the capital A, B, and C. I'm just going to break that down right now. Notice how A and B are lowercase. Notice how this C is big. Anytime you see a big capital letter, that means an angle measure. Anytime you see a lowercase letter, that means a side length. So for example, 30 would be denoted by a capital letter because 30 degrees is an angle measure, whereas something like 8 is a side length. So that would be denoted by a lowercase letter. Okay. And they're basically saying, oh, you could totally find the area if you just use this thing. Well, the bottom line is it says sine of C. All right, we don't know the area, so it's A equals all this. If we could just fill this in with useful information, well, okay, we could just plug it into our calculator and figure it out, right? So turns out that you can. What you need to do is realize that they say sine C, which means that some angle measure is going to be involved. So already we're going to treat this uppercase C as 30 degrees because that's the angle measure that they gave us. Okay. So before I even fill anything in, I'm going to label the triangle and we're going to force that vertex of the triangle to be angle C. Okay. And let's just go around clockwise. So this would therefore be A, and this would therefore be B. Now it all started here because we knew that we're going to use this formula. We're going to have some angle measure here. They gave us an angle measure called 30 degrees. So why don't we go ahead and call this C? All right. We do have the freedom to do that. Now, before we move into this, let's be very clear. We have capital letter A, capital letter B, capital letter C, and each of these big capital letters correspond with an angle, and an angle measure for that matter. Now, some of you have taken trig, you guys know this stuff, but some of you maybe didn't take trig, you don't know it. So you need to understand that if there's a capital letter A, well, the side that's across the triangle, the side that's opposite to that angle, well, that's going to be lowercase a. So lowercase letter a is 8. Similarly, if you have a capital letter B assigned to an angle, well, the side length that's opposite to that angle is going to be lowercase b. And of course, this, due to the same reasoning, 5 is equal to a lowercase c. Now, it turns out we actually don't need that because now we have all the information with a and b equals 4 and all that. We actually have enough information to figure this out. So what we're going to do now is we're going to rewrite it only with our new information. 1/2 times something, we're just going to do empty parentheses, times sine of what c? 30 degrees. Okay. And here is going to be a and lowercase letter a, and that's going to be 8. So we're going to have 8 in there. And this is going to be lowercase letter b, which is 4. 4. And obviously, we're just going to multiply it all up. But you might be wondering, well, what's sine of 30? Well, sine of 30 is something that you could put into your calculator. Okay, so you could use your calculator for that. And that is actually 1/2. Okay, so what I'm going to do is rewrite this whole thing. Only instead of writing sine, sine of 30, I'm going to write 1/2. And this is still 8, and this is still 4. And really, the rest of the calculations are not that bad, right? I mean, let's just think about it. 1/2 times 8, well, that's actually 4. Right? 1/2 times 8 is 4, just looking there only. And then 4 times this 4 is 16. And then 16 times 1/2 is 8. And that would give us the answer as well. Now, just because it took me this long to explain the problem doesn't mean that it will necessarily take you that long to solve the problem, okay? It's conceivable that you could notice this, you could realize the angle that's featured is uppercase C, so the angle measure that's given needs to be assigned with that uppercase C, label it from there, label the rest of the angle and side length measures from there, and then just fill in the cast of characters and then be done with it. So that would have led to the same answer, which is answer choice C. Problem number 60 gets fancy with statistics, concepts, and terms. Some of you might not have a lot of experience with statistics in general. I will say the good news is that the statistics concepts that you need for the ACT are pretty basic. It's going to be very broad strokes stuff. And problem number 60 is actually an example of that. I understand that it says probability distribution. Well, already that's a big scary word. The discrete random variable, that's a big scary word, and then you see this table that has a big X equals a small x and the fractions. And it's just terrible looking. Like, I totally understand that. It turns out that this is easy once you sort of have it explained to you, which I'm going to do. Okay, so basically, I'll just recreate this. So here's the table in essence. I did some dividing lines to sort of separate everything. Okay, I'm going to try to liken this to a real world situation and help you get a sense of what they're really asking for, because they're asking for the expected value, right? So the question is, okay, what does that even mean, expected value? All right, imagine that this is a game at a casino where maybe it's like one of those roulette wheels. I don't really know too much about that stuff, but imagine like a roulette wheel thing where it's like, you get a certain amount of points every time they spin the wheel. Okay, so you can imagine there's this big game and they spin the wheel, and every time they spin the wheel, you get a certain amount of points. Okay, should you continue to play the game. Okay, so you're playing this game, and every time they spin the wheel, you get a certain amount of points. Now, at any given spin of the wheel, you're either going to get 0 points after the wheel spins, you're going to get 1 point maybe for the wheel spin. Maybe you're going to get 2 points that round, maybe 3 points, maybe 4 points, 5 points, or 6 points. So you can imagine probably, 6 points. That'd be amazing because they spin the wheel and it's like you just got 6 points, and that's a lot of points. Okay, so the bottom line is the probabilities over here, these are all probabilities. So this is the chances of you getting 0 points if they spin the wheel. This is the probability or the chances of you getting 1 point if they spin the wheel. This is the chances of you getting 2 points if they spin the wheel. This is the probability that you're going to get 3 points, and so on. And there's literally a 0% chance or a probability of zero that you'll get 5 points. So apparently, getting 5 points is impossible. Okay, that's just impossible. So it's kind of funny how it shows up in the table. Um, but maybe this table actually in reality doesn't have anything to do with a game like that, but we're going to imagine that it does. Okay. Now let's say that some person came up to you and said, it's like, okay, yeah, like they spun the wheel, you got 0 points. Then maybe the next round, you got 4 points on that spin. Maybe on the third round, you got 2 points on that spin. Maybe on the fourth round, you got 6 points on that spin. But what if somebody came up to you and said, okay, well, let's say you played this game forever. Let's say you played this game forever and they spun that wheel an infinite amount of times. What is the average score you would get for each spin? If you played this game forever with infinite spins, what would be the average amount of points per spin that you would earn given each probability? Okay, and that is the expected value. In other words, what is the expected value of points that you would receive per spin if you were to average things out in the final analysis? Okay, now it might be a decimal. Like it might literally be that the average amount of points you would pick up is like 3.3 points per spin. Okay, now it's literally impossible to get 3.3 points because you could either only get 0, 1, 2, 3, 4, 5, or 6 points. But when you sort of add it all up and do the expected value, it might pump out something like 3.3, which gives you an idea that you're going to get, on average, just over 3 points per spin. And then you're going to add it all up at the end, and that would be your total points. So the way to find the expected value is to simply multiply each of these times its probability and then add it all up. Okay, that's what you have to do. You have to multiply each of these and then add it all up. Now, what we're going to do is we're actually going to use this table. We're going to use the table to our advantage. And in fact, you might even want to do that on the ACT just to keep things organized because they already gave it to you in a relatively organized fashion. So here's a nice organized way of going about it. Now, what did I just say? I just said you're going to multiply each of these and then you're going to add it. So we're going to multiply across and put it here, and then we're going to add everything down. So let's start with 0. I'm going to do an asterisk for the multiplication symbol. Okay. And yeah, I'll just do, we'll label it properly. So it's going to be x times p, x equals little x. Okay. So 0 times 1/6, clearly that is 0. 1 times 1/12, well, clearly that is 1/12. 2 times 1/4, well, if you reduce that, that's going to turn into 1/2. 3 times 1/12, that's going to turn into 1/4. We have 4 times 1/12, that's going to turn into 1/3. 5 times 0, obviously, 0. And then finally 6 times 1/3, well, that's going to turn into 2. Now, like I said before, we're going to be adding all of these. And I say we sum them all up and just put the total, the sum down here. Now, many of you can tell that unfortunately we do not have a common denominator. So I see this 12 right here, and everything else looks to be a factor of 12. So let's make 12 the LCD, which is the least common multiple of all of these denominators. So we're going to make 12 the target denominator. Now, we'll actually start here. So this is just going to remain 1/12. This might be weird, but I'm just going to do it for the sake of thoroughness. We're going to make it 0 over 1/12. This one obviously is going to become 6 over 1/12. And being very careful, 1/4, what is that? Well, that would be 3 over 12. 3 over 12. This one, 1/3, is 4 over 12. We once again have 0 over 12. And over here we have 2 equals 24 over 12. So if we were to add all of that up, well, certainly the denominator would be 12, right? But then looking at the numerator, 0 plus 1 is 1, plus 6 is 7, plus 3 is 10, plus 4 is 14, plus 24 is 38. Now, let's say you're pressed for time on the ACT and you just want to, you've made it this far and you're like, okay, well, I just got to throw an answer onto my answer sheet right now. Well, K is the only one that would work at this point because K is a mixed number. And this is an improper fraction. So as you know, all improper fractions could be converted into mixed numbers or, secretly are mixed numbers. It's just a different way of looking at it. And seeing as how answer choice K is the only mixed number in the answer choices, you would indeed be finished if you simply circled answer choice K. Nonetheless, I'm going to briefly review how to do that for those of y'all who may have forgotten. So 38 over 12, improper fraction, which means that it's top heavy. The numerator is larger than the denominator. And the way to handle these or turn them into mixed numbers is to treat them as the division problem that they are. I mean, truth is that all fractions are really just division problems. It's, yeah, it's like 38 over 12. You could see it that way, but it's really just 38 divided by 12. So let's take a look at what that actually is if we do long division. So 38 divided by 12. Well, 12 goes into 38 3 times because 12 times 3 is 36. So it's going to be 12 times 3 is 36. We put 36 here. You're going to subtract that and you will get your remainder of 2. Now, it is the case that the quotient ends up giving you the large number. The remainder is always going to be the numerator, in this case, it's 2, and the divisor will always give you the denominator. And some of you might be wondering, well, that doesn't show up in the answer choices, but in reality, it kind of does because that could be rewritten as 3. And what is 2 over 12? What is 2 over 12? Well, that could be reduced to 1/6, right? So that is why the answer is K. Now, quick recap, expected value, actually not that bad. You just multiply each score times whatever the probability there is of getting that score. So each score times its own probability, and you're going to get a result. Each score times its own probability. And then after you're done with that multiplication process, then you just add up all the results, and that's going to give you the expected value. So that's how you do problem number 60.